In our last video, we refreshed on strategies we had learned in the past to solve systems of two linear equations, two unknowns. In this video, we're just going to take it up a notch and work on solving systems of three linear equations, three unknowns. So I'll share a strategy for the example that you see on the screen here, and then feel free to play around and see how many slightly different strategies you can use in solving just this one system. Before we wrap it up, I'll also show graphically what the solution looks like here. It's kind of fun. Solutions are actually in three-dimensional space because we've got three variables, so that's kind of fun. But let's dive into the actual algebra process. And I've got some notes written here that I'm just going to bring a little further up so we can see them to help guide our process. And again, this is kind of how I like to do these ones. When you have three equations, I want to grab two equations at a time and eliminate one of the three variables. So I've already decided what I'm going to do. Yours could look a little different, but I'm going to start by adding equations 1 and 2 to eliminate z. And then I need to add a different set of two equations. So I'm going to be using equations 2 and 3 to make sure I eliminate z again. So just make sure that you're eliminating the same variable in your two different sets of two equations. Cool, so let's dive in. I'm going to start with adding equations 1 and 2, first of all, because it's actually the easier of the two situations. So I'm going to just copy and paste this down below for us to add and eliminate. So if I add right away, you notice that we're in a good situation here because if we add right away, the negative z and the positive z do in fact cancel. So we just get a 3x and a minus y, no z's, and just a positive 1. And this is a new equation, so I'm going to label it as number 4 so that we remember that this is a good result. Now, I said that the second set might be a little harder only because if I'm looking at equations 2 and 3, just to draw your attention to the z term in equation 2 and the z term in equation 3, if I add those two together, I actually don't eliminate z. And we saw this in the last video too. So the easy fix is you can multiply one of those two equations, or if needed, both, to make the variable eliminate. So what I'm going to do is I'm going to times the second equation by 2, because I know if I had a positive 2 hanging out right here, then that would cancel with the negative 2z term that I see below. So I'm going to leave the third equation as is, and I will times the second equation, what I'm calling equation 2, by a factor of 2. Okay, let me just show that here so I don't make any goofy arithmetic errors. So I'm going to carry down 2 times that equation right down here. Looks like 2 times 2x would be 4x. 2 times negative 3y would be negative 6y. 2 times z is 2z. 2 times negative 1 is negative 2. And then underneath that, I'm just going to rewrite equation 3, no changes made. So just 5x minus y minus 2z equals negative 3. And then let's go ahead and add those up. So we get a total of 9x's, negative 7y's, the z's cancel as intended, and that's equal to negative 5. So I'll call this result my fifth equation. So again, based on how I'm working it, what now has occurred is I can now look at this as a new system of just two equations, two unknowns existing within our system of three equations, three unknowns. To frame this a little better, it's like let's enter at the point where we're asked to solve 3x minus y equals 1 alongside 9x minus 7y equals negative 5. We know how to solve these. That's what we did in the last video. So now we've brought it back to a system of two equations, two unknowns. So let's solve for x and y. Once we get x and y out of this smaller system here, we can then float back to our original system and plug the x and the y into any one of those three equations to obtain a solution for z. So I know that can be a little overwhelming at first, so make sure to kind of track with this process yourself, work through it with me as we're talking through it here. Okay, so again, just to kind of frame our heads here, I'm actually going to draw a line to tell us to look away from the system of three equations and just deal with what remains. So how would we solve this resulting equation? What would be your preference? Feel free to do it in whatever way you see. I'll go ahead and solve by substitution. Sure, why not? So I'm going to go ahead and get y alone in the top equation by subtracting 1 and adding y. And then anytime I see a y in the second equation, I'll just make sure to replace it with that equivalent value. So I'm going to go ahead and work on rewriting my second equation as 9x minus 7, copy and paste 3x minus y as the equivalent expression for, 3x minus 1 as the equivalent expression for y. And now this is just a friendly linear equation, which we know how to solve. So I get 9x minus 21x plus 7 is equal to negative 5. And from there, let's see, 9 minus 21x, that sounds like a negative 12x, right? Plus 7 equals negative 5. I'll subtract the 7 to the other side to get negative 12x equals negative 12. And then out loud, I'm just going to divide both sides by negative 12 to get x equals positive 1. So there is our first solution, our first variable, right? We know there are 3 variables, so we got to keep going. But so far, we know that the x-coordinate of the solution would be equal to 1. We don't have to go too far to find y. I would highly recommend at this point just popping right back up to this substitution equation here to get y. So 3 times the x value of 1 that we just found minus 1 will equal to y. So 3 minus 1 will equal to y. So it looks like y is 2. And what do you know? Pretty quickly there we got our second of the 3 variables. So x is 1, y is 2. Now, using x is 1 and y is 2, we just go back to that original system we were given. You probably have it written down. I'm going to have to scroll back up. But then I'll just sub in 1 for x, 2 for y into any of the 3 equations, and we'll solve for z. So let me scroll back up here. How about we just use the first equation? It looks the least cluttered at this point. So I'm just going to copy down that first equation and sub in the values we just found, which are x equals 1 and y equals 2. And that should allow us to very readily now solve for the third and final variable, which is z. So I'm going to plug in 1 for the x, 2 for the y, z is what we're solving for. So I get 1 plus 4 minus z equals 2, or 5 minus z equals 2. Subtracting 5 from both sides, I get a negative z equals negative 3, or z is equal to 3. So now we've got all 3 of our variables. We know x is 1, we know y is 2, we know z is 3. It's very common to express our solution as an ordered, we call it technically an ordered triple here, because it's not just an ordered pair with x and y, because we have not only x and y, but then we also have z. So we have x as 1, y as 2, and z as 3. Let's look at the graphical representation for this system and the solution, and then we'll call it quits. So thanks for sticking with me. I know these aren't the easiest, but I just have a free app called GeoGebra ready to go here. GeoGebra graphs, this is their 3D calculator, because it turns out when I graph the equations we are given, because they involve 3 variables and they're linear, they're actually planes in space. So I'm going to turn on these equations one by one. This was the first equation, x plus 2y minus z equals 2. So that's the red plane showing there. The second equation is now graphed in green. So you see the green plane is the graphical representation of the second equation. And then I've got one last graph here. Here's the third equation, and that's the blue plane. So I'll just let that spin because it's kind of fun. But what we just found algebraically is these 3 planes intersect at one point. and I'll turn that point on. I have it plotted. X is 1, Y is 2, Z is 3. And that will be the solution that we just found. So if you find this interesting, we study a lot more about three-space in Calculus 3 class, Math 240. So hopefully some of you will go on to take more math. It's actually lots and lots of fun. So there are a ton of applications also of systems of 3 equations, 3 unknowns. I know I didn't mention any of them, but plenty that we could put our heads to and think critically about. So I just turned on the solution. Sorry, I was mesmerized by the spinning image. And you can see that orange point, I'll keep turning it, is the place where the 3 planes all intersect. So that's what we just found algebraically, that orange point labeled A out there. And it's the point where all 3 planes touch. So pretty neat, right? So that's a little bit about solving systems of 3 equations, 3 unknowns. Just a general overview for sure here in college algebra, but down the road you could see some of this getting used again, and you'll probably learn other techniques, including matrices. So we'll call it quits here. Check out tomorrow's videos tomorrow on nonlinear systems.